Hey everyone. Let's see. Today's lecture corresponds to the start of week 4, and remember, so today's Monday. At the end of this week, we've got a midterm exam coming up. We've been talking about determinants. Determinants will be covered on the exam, and so the first thing I want to discuss: properties of determinants. So let's start off with a couple of matrices. So let's let A and B be n by n matrices. Property 1, let's think about what would happen if we took some matrix A, n by n matrix A, multiply it by some constant k. Now that would have the effect of multiplying each row by k, and last time what we learned is if you multiply a single row by k, some constant k, that increases the determinant or multiplies the determinant by that factor k. So if we multiply all n rows by k, what we will get is k to the n times the determinant of A. Second property, and this one's really important. The determinant of A times B is equal to the determinant of A times the determinant of B. So determinants behave very nicely with matrix multiplication. I'm going to put a star by that one. That's an important property. And then one more fact. In general, the determinant of A plus B is not equal to determinant of A plus the determinant of B. So more than likely, if you write down two matrices A and B, add them together and take the resulting determinant and compare that with what you get when you compute them individually and add them together, you're going to get different answers. Let's just see property 2 in action. So as an example, let's say that, let's say A, I'll just do 2 by 2 matrices here. So how about 3, 1, 0, 2, and B is the matrix 1, minus 1, 1, 0. So if we multiply out AB, 3, 1, 0, 2, and then 1 minus 1, 1, 0, that's going to give us, let's see, that'll be a 4. That will be a negative 3, and we'll get a 2, and then we'll get a 0. So the determinant of A times B, that's going to be 0 minus negative 6, so we get a positive 6. And so if we do them individually, what do we have here? We've got the determinant of A, right, so determinant of A times determinant of B, that's going to be a 6 times positive 1. All right, so we get 6. All right, so they're a match. That's what we'd expect. This is not too hard to prove. They prove it in their book. If you want to go through the proof, you can. So now, let's say note. If E is an elementary matrix, then, okay, so remember, an elementary matrix is one that's been obtained from the identity matrix by performing a single elementary row operation. Maybe we interchanged 2 rows, maybe we multiplied a row by a constant, maybe we added 1 row or a multiple of 1 row to another row. In any of those cases, what we have is the determinant of E is non-zero, right? Right, just think about it. The identity has determinant 1. Any one of those 3 row operations is going to affect the determinant, but in a way that will not introduce a 0 for its determinant. Now, so let's say if we have some invertible matrix A, then what do we know? One of our properties, one fact that we know is that A is equal to the product, let's say E1, E2, dot, 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 up through E sub k, where each one of these matrices is elementary. So where each E sub I is elementary. So now, using property 2 that we had written down a minute ago, if we look at the determinant of A, that's going to equal the determinant of the product E1 dot, 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 up through E sub k. And the determinant works nicely with matrix multiplication. This is equal to the determinant of E1 times dot, 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 times the determinant of E sub k. Each one of these matrices has a non-zero determinant, which means that their product is non-zero. So what we just proved, and I'm going to write this as a theorem, the matrix capital A is invertible if and only if the determinant of A is non-zero. A few of you have actually asked this question. When are we going to find out what, how do we determine whether a matrix is invertible or not? Prior to this moment right here, what you would have to do is set up our algorithm, have A on the one side, the identity on the other side, start row reducing and see if you can get the identity on the left-hand side. If you can, then you know that your matrix is invertible, right? Well, you may or may not want to do that. Here's another, say, quicker test, even though determinants can be a little bit slow, if it's a really big matrix. The matrix A is invertible if and only if the determinant of A is non-zero. Now, what I want you to do, all right, we have this theorem called the equivalence theorem. All right, so if you remember, you don't need to write this down. Hopefully, you've already started your list. So the equivalence theorem, so far, we have part A, that was A is invertible. And then there are a bunch of equivalents that are equivalent, a bunch of statements that are equivalent to A being invertible. I can't remember which one was F, but now we're going to add, so far we should have A through F. We're going to add one more to that list now, and that is determinant of A is non-zero. So if the determinant of A is non-zero, then A is invertible, and vice versa. Vice versa, if A is invertible, then the determinant of A is non-zero. Here's one fact I want to think about. So let's say, suppose that we've got an invertible matrix. So suppose A is invertible. So then, all right, what does that mean? That means that A times A inverse is equal to the identity. And so, okay, now I'm going to take the determinant of both sides of this equation. So what we will get is determinant of A times determinant of A inverse is equal to the determinant of A times A inverse, which equals the determinant of I. So what I did right here, this is taking the determinant of this equation. On the left-hand side, I'm using our property, our multiplicative property of determinants. And then the determinant of I is equal to 1. So what we did, we just proved a theorem that tells us the relationship between the determinant of a matrix and the determinant of its inverse. Right? So if I take this equation right here and solve for the determinant of A inverse, here's what we get. If A is invertible, then the determinant of A inverse is the reciprocal of the determinant of A. Right? Just solve for the determinant of A inverse and you get this equation right here. All right? We know when A is invertible that this fraction here makes sense because we know the determinant of A is non-zero. We have an algorithm right now for finding an inverse matrix. Remember how that goes? Right? You write A on the left-hand side, you write the identity on the right-hand side, you do some row operations so that you get the identity on the left-hand side, and you'll be looking at the inverse on the right-hand side. So we've already seen that. That's our procedure for finding inverses. I want to go through another procedure. So let's say finding inverses, part 2. This will be an alternate way to find the inverse of a matrix. Sometimes it's quicker, sometimes it's more useful, or let's say more efficient than our previous algorithm. So here's how it goes. I need to remind you. So let's recall if A is n by n, and let's say capital A sub ij is the n minus 1 by n minus 1 matrix obtained by deleting the ith row and jth column. So remember, when we were learning about determinants, we introduced this notation right here. If you have a matrix A, capital A sub ij is the matrix that you get by deleting the ith row and the jth column. And then C sub ij we define to be minus 1 to the I plus j times the determinant of A sub ij. This was the ijth cofactor. Now what I'd like to do is actually, I want to create a matrix. So we form the matrix of cofactors. And so that goes like this. C is going to be equal to C11, C12, dot, 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 C1n, Cn1, Cnn. So this matrix of cofactors is the n by n matrix that you get by writing cofactors in each of the corresponding positions. So this is called the matrix of cofactors. And then we'll say definition, the adjoint of the matrix A is, and we write this ADJ of A, and it is the transpose of the matrix of cofactors. That has a special name, right? It's called the adjoint. Okay, now why would we care about this matrix right here? Well, the following theorem tells us why. So if capital A is invertible, then A inverse equals 1 over the determinant of A times the adjoint of A. So this right here, this formula gives us an alternate way to find the inverse in the case that our matrix is invertible. So how would you use this in practice? You would say, okay, here's my n by n matrix A. Compute its determinant. If you get non-zero, then you know that your matrix A is invertible. Then you can go about finding the matrix of cofactors, compute its transpose, and set this matrix up. You're looking at the inverse matrix. Okay, now let's try an example of seeing this algorithm in action. So let's take a 3 by 3 matrix A. It's going to be 1, 3, 1, 2, 1, 0, and 1, 0, 1. First thing we're going to need, we need the determinant of A. So determinant of A is equal to, let's see, that will be a 1 times 1 minus 3 times 2 plus 1 times negative 1. So that gives us negative 6. Since the determinant of A is not equal to 0, we know that A is invertible, so this process is going to work now. Next, I need to write down all of the cofactors. So C11 is going to be, well, okay, officially it's going to be minus 1 squared, right? That's, in fact, let's write it out. This minus 1 to the 1 plus 1, right? Add those right there. That's going to be the exponent on minus 1, times the determinant that you get by deleting the first row and first column. And that resulting matrix, that little square right there, gives us the determinant of 1. So C11 is equal to 1. C12 is going to be negative 1 raised to the third power. And then I delete the first row, second column, and that gives me a determinant of 2. So C12 is equal to negative 2. C13 is positive 1 times negative 1. Make sure I'm getting that right. Okay. Now C21, that's going to be a negative 1 raised to the 2 plus 1, so the negative 1 to the third is a negative 1, times the determinant of the matrix that you get by deleting the second row and first column, and that looks like a 3. C22, negative 1 raised to the fourth power, so that's a 1. And then if I delete second row, second column, I get 1 minus 1, which is 0. C23 will be a minus 1 times, so delete second row, third column, that gives me a negative 3 here. And then now we move on, so C33 is going to be a 1, negative 1 to the 6th, so 1, and then delete third, this should be a C31. So that's going to be a 1 times, delete third row, first column, and I get negative 1. C32 will be a negative 1. Delete third row, second column, negative 2 times negative 2 here. And then C33 is going to be delete third row, third column, and I get a 1 minus 6, negative 5. So let me just check all my numbers here. 1, negative 2, 1, negative 1, negative 3, 0, positive 3, negative 1, positive 2, negative 5. Yep, okay, so those are the cofactors. So now, A inverse is going to equal 1 over the determinant of A, so that's a negative 1/6, times the adjoint, which is going to be the transpose. And you see I wrote this in matrix form, so I'm going to write now this, when I take the transpose, right, this is going to go 1, negative 3, negative 1, and I'm going to write that 1, negative 3, negative 1. The second column here becomes the second row here, so this will be negative 2, 0, 2. Negative 2, 0, 2. Negative 1, 3, negative 5. Negative 1, 3, negative 5. Yeah, okay, and then if we multiply through, we will have the matrix negative 1/6, 1/2, 1/6, 1/3, 0, negative 1/3, 1/6, negative 1/2, and 5/6. So I don't know which one takes less work or more work. It has the advantage. Somehow it's maybe easier, or it's easier to do this one without screwing up. I screw up row operations quite a bit. I make arithmetic mistakes. Maybe this one's slightly easier to do. But what we have now, 2 different ways to compute inverse matrices, right? And you can use one or the other depending. I'll just say it's a matter of taste.